I thought it might be interesting for you to hear what it's like at the boundary between basic science and application engineering. I was very fortunate. I was working on my graduate thesis on a topic of how the physics inside of a transistor affects its behavior in a circuit when you use it as a switch, like in a switching power supply or in a logic circuit, something like that. It turned out there were lots of papers, equations ad nauseum, analyzing how these transistors worked when you used them in amplifier circuits like your hi-fi. But nobody had looked carefully at what happened when you used them as a switch. And of course, in today's world, that's what most transistors do. In those days, it was not so clear, but it was a very interesting thing to look at. So I was in the middle of that, and deep in this boundary between the physics of inside the transistor and the circuit and how it behaved and what you might do with it. I was just finishing up my thesis when there appeared a paper by a Japanese researcher by the name of Leo Asaki. And he had invented a device that worked by electron tunneling. Now, electron tunneling is a quantum phenomenon. It's one of the very basic properties of an electron, that it behaves like a wave when you get close enough up to it. And electron tunneling allows an electron to penetrate through a barrier that it couldn't normally get through, but it can tunnel through if the barrier gets thin enough. And so that was a very interesting thing to me. I had heard about tunneling in physics courses, but the examples were always kind of things like radioactive decay. Well, radioactive decay is interesting, but you can't do anything with it. You can't change it, you can't change the barrier, you can't, it just, you observe it and it's done. But here was an electron device that actually did useful work, and it worked on this principle. So I got fascinated by this quantum phenomenon, electron tunneling, and it ended up, I spent the next 12 years of my life working on it, and I got the graduate students involved, and we did a lot of work on tunneling through thin insulating films, tunneling in junctions between metals and semiconductors, all of those kinds of things. And in the process, we had to learn a lot about how to measure the energy of the barriers that the electron was tunneling through, and there was a lot of just basic experimental work that was going on. Well, I was just getting started with that, and one day this guy walked into my office and said, "Hi, I'm Gordon Moore from Fairchild." Well, I had heard of Fairchild, of course, because they were making some of the leading edge transistors, but I'd never heard of Gordon Moore. But he says, "What are you doing?" So I told him a little about the work on tunneling, and he said, "You're teaching the transistor course, aren't you?" And I said, "Yes." And he said, "Do you have a lab with that course?" And I said, "Yes, of course. I wouldn't teach a course like that without a lab." So he said, "Would you like some transistors to use in your course?" The answer to that was pretty obvious. In those days, the transistors we could buy cost $1, which is a lot of money for a grad student. And they were very poor transistors. They didn't work very well. And here were these high-performance transistors that he offered me a big bag of. So, well, that got my attention right away. And so we talked some more about what I was doing, and he said, "Why don't you come up and give a seminar at Fairchild?" And so that was very exciting for me, because I knew they were doing leading-edge work in the late 50s, early 60s. And this was around 1960 that this happened. So I went up and gave my talk and went out to dinner with a few of the Fairchild founders, and they said, "Would you like to consult with us?" And once again, I didn't have to think twice. I said, "Sure." And that began a weekly commute up to Silicon Valley from Pasadena, where I was teaching. And it was a very interesting experience because here were a bunch of really smart people that were grappling with very real problems of producing large quantities of these leading edge transistors. They had a production process that had never been done before. They were fighting all kinds of problems with the basic nature of the transistors. And the thing I found right away was that any time you have a leading edge technology you're pushing, you will uncover fundamental questions that there aren't answers to in the literature. When you first look at the literature, it looks overwhelming. It looks like everything has been done and everything that needed to be known is already known. And it turns out that's only an illusion. When you get right down to doing a real thing, it simply isn't understood. No matter how many papers there are and how many equations they heap on it, they don't know what's really going on, and you have to figure it out. So I would come up with these really neat fundamental problems by working with the guys up at Fairchild and go back and work with my grad students and do the fundamental physics. And that ended up being an extraordinarily productive 10 years or so. Gordon Moore is a wonderful human being, and he's an early riser like I am. So he would get to the Fairchild lab about 7 o'clock. And so on my consulting day, I would come in about 7, and we would have an hour before anybody else showed up to talk about what was going on and things he'd like me to look at. And I remember very vividly in 1964 or so, he'd been making this plot. They had built the first integrated circuit in 1959. Bob Noyce, co-founder with Gordon, had figured out how to use the process they already had for making transistors and hook the transistors together on the surface of the piece of silicon and make a working circuit, all on one piece of silicon. Whereas before they have to cut the transistors up and put them in packages and wire them up and then put them back on a circuit board to make a circuit. So there's a huge economy if you could make the circuit right on the silicon. And Bob was the guy who had figured that out. Gordon had observed that as they developed the technology, about every year, the number of transistors they could put on one of these circuits would double. And just in the natural course of people figuring out the kind of circuits they wanted to build and designing them and getting them to work. And this was a thing that had gone on for 5 or 6 years by then. And he'd been making this plot, and every once in a while I'd say, "Gordon, could I have a slide of that so I could show it to people?" And when I'd go around and give talks, I would always show Gordon Moore's plot. And one day we were sitting there, and he said, "Carver, you're working on electron tunneling. Now that happens when things get very small, right?" I said, "Yeah, that's right." He said, "Well, won't that limit how small you could make a transistor?" And I said, "Well, yes, of course it will." He said, "Well, how small is that?" So I stopped and thought about it. And I said, "Well, if you're making MOS transistors, when the gate oxide gets thinner than about 100 angstroms, 10 nanometers, then you'll start to get gate currents, and if you get too much gate current, it won't be an amplifier anymore. But that's a long way from the size transistors we're making right now. I said, let me go work with one of my grad students, and we'll figure out exactly how that's going to work. That got me thinking. It was an excellent question, of course. A couple of years later, I got invited to give a talk at a IEEE workshop. Every year they had these workshops for people working on device physics. And in those days, it was a small club. There were maybe 100 of us in the U.S. that worked on that stuff. We all pretty much knew each other, and we'd get together once a year at these workshops and talk about the latest things we'd done. And I thought I would talk about what I'd been thinking about scaling the circuits better. We knew a lot about the fundamental physics of the transistors by then. It turned out if you scaled them down smaller and smaller, something very interesting happened. Now, there were papers throughout the literature saying that if you made them much smaller than they were at that time, that the power would get so big that it would melt the silicon, or the cosmic rays would get you, or one thing and another. But there was nothing that I could find in the fundamental physics that would stop us until they got maybe a factor of 20 or 40 or maybe even 100 smaller than they were at that time in linear dimensions, which means there would be 10,000 times as many per unit area. Something very amazing happened. If you scaled it just right, you scaled things horizontally, of course, so you could put more on the chip. But you had to scale it vertically because otherwise the device wouldn't work. And then because you scaled it vertically, you had to keep the electric fields from getting too high, so you had to cut the voltage down. And if you did all that just right, it turned out you not only got more transistors, they all worked faster, and they took enough less power that the power per unit area stayed constant. So there was nothing to stop you until you ran into the basic physics. And it was astounding how much faster they got. I kept saying, look, this can't be true. Murphy always has a way to stop you on stuff like this, but I couldn't find it. So I gave the talk. And of course, everybody was yelling and shouting. I didn't know what I was talking about. I had forgotten about this and that and the other and all of that. But in the end, by a year later, we had another workshop, and 2 or 3 groups had gone and done the calculations themselves and corrected some little factors that I had so that they could add value. And then was the first time that we had a scientific basis for the belief that Gordon Moore's vision of having ever more transistors on a chip could actually be realized with physical transistors. And so that then created a belief system that caused the industry to adopt a process of continued scaling, which they're still on today. And the whole thing became known as Moore's Law. And the information technology that we all enjoy today is benefited tremendously from that phenomenon. So that was an example of where some very basic physics applied to a very real problem in a very real industry that was pushing the edge made a big difference. And to me, that was a great experience, of course, to be able to participate with the guys that were actually doing the work of building those transistors and designing those integrated circuits. So I wish I could report to you that our technical progress in not only the information technology but other technologies worked that way. I have to tell you another story that happened to a friend of mine, Charlie Towns, who unfortunately is not with us anymore. But Charlie's the guy that invented the stimulated emission devices, lasers and masers, that we all enjoy in our communication systems and in our DVD players and all of technology, is the pointers we point at the screen with, all of those things. Charlie came up with this idea shortly after he got his PhD, and he had guts enough to go talk to Niels Bohr and Werner Heisenberg, who were the two founders of quantum mechanics, the same quantum mechanics that we torture our students with today. And unfortunately, it hasn't changed much. And so Charlie went to them, each separately, and described his idea for making coherent radiation by making a stimulated emission device. And each of them separately had said to Charlie, "Oh, Sonny, you just don't understand how quantum mechanics works." And of course, the reason they said that was because they had conceptualized the quanta of light as being little bullets of light that came out of an atom and hit another atom. If that's the way it worked, you could never make a laser work. And if you did get a laser that worked, it would never be capable of cooling down atoms to the point where they make a Bose-Einstein condensate, which is the way atoms are cooled today to make those nanokelvin temperatures that make the Bose condensate work. You all know that when it rains heavier, the sound on the roof doesn't get quieter. Well, if the photons were little bullets, the more of them you had, the more noise you'd get. Doesn't work that way. So it wasn't Charlie that didn't understand how quantum systems worked. It was the guy who had ginned up the hokey kind of theory that they'd come up with, which gave the right answers when you had a statistical kind of thing like a glowing gas, but was totally incapable of coping with systems like lasers. Well, fortunately, Charlie was not easily dissuaded, so he went back and kept working and got his maser to work. And he and his collaborators were hard at work on getting an optical version of the laser when Ted Maiman down at Hughes Research Lab actually went and created one. And that's all history now. We all have lasers and think nothing of them. But here were the scientifically best respected people in the field actively dissuading this young man from building a historic device that's absolutely key to our information technology today. That's the flip side of how, quote, fundamental science, when it's not coupled closely to the real world, can actually retard progress. So both things happen. Both things are happening today. Fortunately, those of us who are working with quantum systems had to figure out our own way of thinking about them, because the standard way that Bohr and Heisenberg and the people after them had formulated a thing, didn't work for what we were trying to do. We all had to sort of hack it together our own way. We're still having to do that. And it's a good thing. We have people out there building real communication systems, building real optical systems. Many of you know that today we can basically do all of the coherent processing that you do in radio at optical frequencies. It's absolutely astounding. And there are no little bullets of light to get in the way, fortunately. That's two aspects of the way science and technology evolution work with or against each other. And we'll see how it plays out in the future. You just hope that there are enough people building real things and figuring the stuff out for themselves that they keep ahead of the fundamental scientists who want to write enough equation to slow them down.